Alright, this is section 2.3 of Algebra 2, solving linear systems graphically. A linear system is a system of two or more equations with the same variables. Normally we see x and y, and the highest power of x will be to the first power, and so will the highest power of y. And where they cross, their point of intersection, is the solution for that system of equations. So the solution is a point. It's an x value and a y value. So when we're given something like number 1 and 2, where it says determine whether or not the given point is a solution to the system of equations, what we need to do is put that point into the equation. So we take and we substitute that point into our system of equations. So what you have to do is, for the x is negative 2, so you have in this first one negative 2 minus 6 times 3 equals 20. And then that's minus 2 minus 18 equals 20, which we get negative 20, equals positive 20, which is not true. They do not equal each other. So all it takes is for one of them not to work out. Since that first didn't work out, the answer is no. That point is not a solution to the system of equations. For 4, negative 9, we substitute into this first equation. 11 times 4 minus 2 times negative 9 equals 62. Okay, so you have 44 plus 18 equals 62, and that is correct. 62 does equal 62. Okay, so the first one checks out. Now we have to make sure it works for both of them. So we go to the second equation. 3 times 4 plus negative 9 equals 3, which is 12 minus 9, which of course is 3. So it checks out for both equations. This point plugged in gives us a true statement for both equations. So yes, it is a solution set. It's a solution for the system of equations. Now another way to solve them is, if you don't know the point, you can graph each equation. And of course, the way to graph is to either get y-intercepts or to make them y equals lines. So if we have x minus 2y equals 5, okay, you can leave your 2y here and subtract x across. Negative x plus 5. Dividing by negative 2 then, in both places here, will give you positive 1/2 x minus 5/2. Now put this in your calculator if you have a calculator, or you can sketch it on your graph. But that one is going to look something like this when you put that line in. And I don't draw real straight lines with this pen. Now let's look at our other line. We have 4x plus 3y equals 9. Leave the 3y here and subtract the 4x from both sides. So you have 3y is equal to negative 4x plus 9. Dividing by 3, you have y is equal to negative 4/3 x plus 3. So up here at about 3, we're going to cross the y-axis, and it's a slope of negative 4/3. So it's going to come in something like that. Okay. Then you can go on your calculator, how we've learned before, and actually get the intersection. And if you remember that second, and then trace, because that gives you the calc menu. And then you go to intersection. I want to find the intersection, and then enter, enter, enter 3 times. And we find that our intersection right here where they cross, and I didn't do the greatest job of sketching, is 3, negative 1. And that's our answer. X equals 3, y equals negative 1. And when it is graphed especially, you need to state your answer as a point rather than a x equals and then y equals, because the graphing, the solution set is that point where they intersect. Okay. Let's go to our next set of notes. Move down a page. Okay. In this set, we're going to graph these lines again. We have to make them y equals lines. So 3x plus 8y equals negative 32. We have 8y is equal to negative 3x minus 32, dividing by 8. Y is equal to negative 3/8 x minus 4. So down here, and we'll sketch the line something like this. Now you can put it in your calculator to do this again. Okay, then our next line is 9 minus 2y equals negative 22. Negative 2y is equal to, and that should have been 9x, excuse me, negative 9x minus 22. And dividing by negative 2, then we have positive 9/2 x plus 11. So way up here at 11, we have a line, and we're going to draw that down, something like that. And your point of intersection right here will be negative 3.077 and negative 2.846. So this one doesn't have a nice even solution. You can round it to hundredths. You can round it, leave it at thousandths. I wouldn't carry it any more than 3 places, but it's okay if you round it to hundredths. Okay, for me. So that would be our point of intersection, which is again the solution to this system of equations. So now we're going to do a couple more examples. On this one we have 6x plus 4y equals negative 12. So we're going to leave the 4y and subtract the 6x across. Okay. We divide by 4. That's going to be negative 3/2 x minus 3. Okay. So that's going to come in here something like this. Okay. On this equation, second one, number 2, you have 2y is equal to negative 3x plus 1, divide by 2, and you have negative 3/2 x plus 1/2. And you notice the slopes are the same, so those should draw and graph as parallel lines. Alright, this is it. This is 1, and this is 2, and this is line 1, and this is line 2. If we wanted to put subscripts to show the different lines, then that's not a bad way to do that, y1 and y2. Now, since they never cross, parallel lines are no solution. Or there's an empty set. There's no solution to that system of equations. Now looking at this next set, we have negative y is equal to negative 2x plus 5. I'm sorry about the slamming doors, but that's, maybe you don't hear it too much. Now we divide by negative 1 or multiply by negative 1 across, so you have y is equal to 2x minus 5. Okay, so that's going to graph something like this. Probably crosses a little farther down if you're sketching it. Now on the second line, this is line 1. Line 2, you have 3y is equal to positive 6x when we bring that across, minus 15. And then dividing by 3, you have 2x minus 5. Well, these are exactly the same. This is an identity where you graph it, and they're exactly the same. And so this answer is infinitely many. Now, not every number is a solution, so you don't want to put like all real numbers because points out here aren't a solution, but there's infinitely many solutions that run along that same line. And so that is your answer. There's infinitely many. y1 is the same as y2 if they're equal. And that is the end of 2-3.